Today you are going to learn how to use matrices to represent linear transformations in 2 dimensions, such as rotations, reflections, enlargements, and stretches. A 2x1 matrix, which is usually called a vector, can be used to represent a coordinate. So instead of writing it in its column vector form, we can write it in the coordinate form. Plotting these 3 coordinates on the coordinate grid gives us a right-angled triangle. Now we're going to transform this. So we're going to perform the matrix multiplications using the matrix 2, 0, 0, 2 and multiplying by each of the vertices of that triangle. So if we look at that first one, 2 times 1 plus 0 times 1 gives us 2, and 0 times 1 plus 2 times 1 gives us 2. So the coordinates 1, 1 are mapped to 2, 2. Let's see this on the grid. So 1, 1 is mapped to 2, 2. If we continue with this, so 2, 0, 0, 2 multiplied by 1, 3. This gives us 2, 6. So the top corner this time is mapped to 2, 6. And the final one gives us 2, 1 being mapped to 4, 2. So this is the last vertex is mapped to this position here. Now can you see what's happened? The matrix 2, 0, 0, 2 represents an enlargement by a scale factor of 2. These 2x2 matrices represent geometrical transformations. We're going to use the coordinates 0, 0, 2, 0, 0, 1 and 2, 1 to work out what they represent. Now, it would be a good idea at this point to stop the presentation and copy down these matrices, or take a photo of this so that you can work with it as we go forwards. I will work through a couple of examples and then you can have a go at the rest yourself. Let's take a look at what this matrix 2, 0, 0, 1 represents. We're going to position the 4 coordinates on a coordinate grid and label them up A, B, C and D. As you can see, they represent the vertices of a 2x1 rectangle. And if we apply the 2x2 matrix over here, the 2, 0, 0, 1 to each of those 4 corners, we will see how they're transformed and then be able to describe the transformation that has taken place. Now we can do this individually on each corner by entering in the coordinates of the vertex here, or we can list all of the coordinates, all of the corners in a 2x4 matrix and perform all of the calculations in one go. Okay, now we need a line going across and some lines going down here, and multiplying these together gives us this as the result. And I'm going to label these A prime, B prime, C prime and D prime. I'm going to take a look at how A has been mapped to A prime, B to B prime, C to C prime and D to D prime. So A is 0, 0 and we can see A prime is also 0, 0. So no movement has taken place there. B 2, 0, so this coordinate has been transformed to the coordinate 4, 0, which is just over here. C has gone from 2, 1 to 4, 1. That's up here. And D has transformed from 0, 1 onto itself, 0, 1. So this remains in the same position. So what we can see now is a larger rectangle where the height has remained the same, but the base there has been multiplied by a scale factor of 2, and therefore this transformation 2, 0, 0, 1 represents a stretch along the x-axis by a scale factor of 2. Let's take a look at the matrix 1, 0, 0, minus 1 and its effect upon the rectangle with vertices at A, B, C and D. So again, I will just label up these points A, B, C and D. And we're going to perform the calculation in the same way as we did with the last example. So if we line up each of those coordinates again, A, B, C and D, and perform that multiplication, that takes us to, again, we'll call these A prime, B prime, C prime and D prime. Let's have a look at the transformation now. So A started at 0, 0 and again it maps to itself here. So we'll call A prime and B 2, 0. Now this one's staying the same this time. So let's put B equal to B prime. And then let's have a look at the next one there. So C 2, 1 is mapped to 2, minus 1. So 2 minus 1 is down here. So this is C prime. And then the final one on there, so we have 0, 1 is mapped to 0, minus 1. And that is down here. So that is D prime. So now if we join those four corners together, so we have a, just do it a little bit larger, so we have a rectangle. It's the same size as the original rectangle. So the red one has been transformed and mapped onto the yellow one there. Can you see what has happened? The size is the same, but the position is different. Now it's important to understand that the labelling of each of the corners here does make a difference to what the transformation would be. So because A has remained the same and B has remained the same, this transformation is a reflection in the line y equals 0 or the x-axis. That's the first two completed. Now have a go at the rest following the same method as shown in the previous two examples. Stop the presentation here, work through, and then I will reveal the answers. If you know the transformation, then you can work out the transformation matrix by using unit vectors. The unit vectors are 1, 0 and 0, 1. Now 1, 0 is denoted by I, which can be written in this form with a line underneath, and 0, 1 is represented by J, just like this. Now if we were to draw these on a coordinate grid, then I would look something like this, and J would look something like this. So it's one across on the x direction and one up on the y direction. What is the matrix M that represents a reflection in the line y equals x? We need to see what happens to the coordinates of I as it undergoes this transformation. So the coordinate of I is 1, 0 and it is mapped to 0, 1. Similarly, if we take J has coordinates of 0, 1 and it is mapped to 1, 0. So the coordinates of I transform to the first column of the matrix M, and the coordinates of J transform to the second column of the matrix M. So the matrix 0, 1, 1, 0 represents a reflection in the line y equals x. What is the matrix M that represents a rotation of 90 degrees anti-clockwise? Again, let's take a look at what I will transform to. So it will transform from 1, 0 to 0, 1. And what about j? Well, j moves down to the negative x-axis and so is mapped to -1, 0. And it's these two vectors that make up the matrix for the transformation. So 0, -1, 1, 0 represents a rotation of 90 degrees anti-clockwise. What is the matrix M that represents a rotation of theta degrees clockwise? Let's see where I is transformed to. So as it rotates round by an angle of theta, its distance away from the origin remains 1 as it was a unit vector. Now if we make a right angle triangle here, we can use trigonometry to work out the coordinates of this point. This is cos theta. This comes from the adjacent being equal to cos theta multiplied by the hypotenuse. This length represents the sine theta as the opposite is equal to sine theta times by the hypotenuse. And we know that the hypotenuse of this triangle is 1. So I will transform to cos theta minus sine theta. So be careful with the signs on this one. Now let's take a look at what j transforms to. I'll just get rid of the writing at the bottom there. As A rotates round by an angle of theta, its length away from the origin remains the same, so this is also 1. And if we draw in a right angle triangle again, we can work out the length of each of those sides and therefore the position of where j will be transformed to. So this represents cosine for the same reason again, so the adjacent will be equal to the cosine theta times by the hypotenuse, which is 1. And similarly for the other side, we have the opposite is equal to sine theta times by the hypotenuse. And so j is transformed to sine theta cos theta, and therefore M is represented by the matrix cos theta sine theta minus sine theta cos theta. What is the matrix M that represents a reflection in the line y equals tan theta x? Now there's a lot to unpack with this question. First of all, we need to understand that tan theta represents the gradient of this line. So in order to do this, I'm just going to draw a diagram here. So we know that this angle is also theta. If we wanted to work out the gradient of this line, we would need to know this length here, the change in y, and the length across the bottom, the change in x. And the gradient would be equal to y over x, so the change in y divided by the change in x. Now if we use trigonometry, the length of y here would be represented by the opposite, and x would be represented by the adjacent, and so the opposite divided by the adjacent would give us tan theta. And we know that the opposite is y and the adjacent is x. So the gradient of this line has the same value as tan theta. Let me clear the diagram. Okay, so this is just representing the gradient, which we could call M. Now let's take a look at how I is transformed. As it's reflected through the line y equals tan theta x, it's reflected at 90 degrees through this line. Now we know the position of I from the origin has a distance of 1 or a length of 1, and therefore to its transformed position this also has a length of 1. We also know that the angle here up to the line of reflection is theta, and therefore the larger angle must be 2 theta. If we drop a line going down, if I move this one here, we can work out the lengths of the adjacent side here and the opposite here, just using trigonometry in a very similar way to what we did last time. I'll just clear this diagram a little. So the adjacent is cos of 2 theta, and that comes from the adjacent being equal to cos of the angle, which is 2 theta, multiplied by the hypotenuse, which is 1. The opposite is equal to sine of the angle, which is 2 theta, multiplied by the hypotenuse, which is 1. So I is transformed to cos 2 theta, sine 2 theta. We remove the annotations again. And let's take a look at how J is transformed. Again, as it reflects through the line, this is meeting at an angle of 90 degrees. And we know this length here must also be 1, as the length of the origin to J would be 1. And if we form a right angled triangle from this point to the x-axis, we know this angle is 2 theta. Now this angle comes from the fact that we know this angle is theta, and as you work through this, because we're dealing with lots of right angled triangles here, it means that this angle here is theta, and because this would then represent an isosceles triangle, this little angle would be theta, and therefore the bigger angle would be 2 theta. We can use trigonometry in the same way to work out both of those lengths of that triangle. So the adjacent would be cos 2 theta, and the opposite would be sine 2 theta, in a very similar way to how we worked it out for I. And that means that J would be transformed to sine 2 theta minus cos 2 theta. So just be careful here with the negative being the position below the x-axis. These are the general 2x2 matrices that can be used to represent these transformations. So the first one is an anti-clockwise rotation by an angle of theta degrees about the origin. This one is a reflection in the line y equals tan theta x. These are in the formula book. You don't need to be able to derive them, but it is nice to see where they do come from. And then we have some others. So this is a stretch along the x-axis by a scale factor of A. And this one is a stretch along the y-axis by a scale factor of A. And here we have an enlargement by a scale factor of A. Please turn to page 170 and complete exercise 8A, and then page 175 to complete exercise 8B.